Hello everybody, welcome to my presentation on ontology design principles for model-driven applications. What do I mean by model-driven applications? This is a space that I have worked in for some time, where you use ontologies as standardization artifacts among people to thereafter build other systems from. And in these scenarios, you typically don't deploy your OWL file as is, but rather you run it through some translation process to get out a representation that can be deployed in the target runtime environment. And this could be something like an OAS spec, also known as a Swagger, to generate a RESTful API. It could be something like C# or Java code, or other source code for that matter. Could be even Excel sheets. In my case, I worked particularly with something called DTDL, or Digital Twin Definition Language, which is a Microsoft spec for how to build digital twins and smart buildings. And when you do this, you typically want to run this through this translation process, because as the OWL ontology evolves and as this standard evolves, you don't want to have to keep track of changes manually in the deployment artifacts, but rather you want them to be generated from the source automatically. And in order to do this, it gives rise to some trade-offs, if you will, in ontology modeling, which this paper is about. Now, before we proceed, just a general word of caution. What I'm presenting here and in the paper are, I think, reasonably well-grounded opinions based on my personal experience across multiple projects. The examples that I give are mostly from my work on the real estate core ontology, which is seeing some quite substantial adoption in some real estate markets in Northern Europe. But, this is personal experiences. You may be cleverer than I am. You may have a greater understanding of, and I'm sure you do have a greater understanding of your specific domains than I have. So take this with a grain of salt and take the context that you are working in into account. There is, in ontology modeling, as in all other conceptual modeling, very rarely just one truth. So this is an opinionated position paper. Going forward, I'm going to go through 8 principles that I have found to be helpful to consider in such modeling work. Principle number 1, cognitive clustering classes and why they should be avoided. So what you typically find in ontology engineering quite often is that ontologists create classes that aren't actually needed per the requirement spec, but that give rise to a nice looking tree structure in a tool such as Protégé. So in this case, this example here, the class information on the bottom right there is actually not needed or used in the real resulting artifacts. It was actually created just as a nice nesting point for all the subclasses there. And the problem is that if we add a class such as this and then run it through some tooling, it may blow up in terms of the files that it generates, and it may end up that you need to have tests added to these artifacts that are created, documentation and so forth, version management, etc. And it simply adds a bunch of potentially unneeded complexity. So here the guideline is, and the principle is, if there are no specific semantics that apply to a given intermediate class in the hierarchy, don't use it. And in this case, if we could have properties perhaps that point to or point out of information individuals, then it might be useful to keep it. But as it happens, we don't. So this ought to be removed. Principle number 2, create classes for concepts that carry identity. So non-ontologists working with code or data models or what have you typically represent data attributes using fields or data properties on things that have identity. Right? So if you have something like an event, you would have that as your class-like representation or your schema representation or whatnot, and you would have fields on it to represent the starting and ending date or date time or time. Ontologists, on the other hand, we often generalize or optimize sort of spatiotemporal relations, for instance, such as in the case here, the time interval, which is given its own class. And then you would connect the time interval onto your event, and then you would add the data fields onto your time interval. Or in the lower right-hand corner, this notion of geometries. So some spatial thing has a geometry, and that geometry then has a representation. And I'm going to call this an anti-pattern in this context. Not necessarily always, but in this context it becomes a bit of an anti-pattern. Because when you talk to developers who want to deploy this in their schemas and their systems and their source code, generally they find this entirely confusing and prefer not to use it. So generally, if possible, connect your data fields directly onto your real-world things or your things that have some notion of identity. Principle number 3, use OWL classes for typing. Perhaps you already do this, possibly you do. There is a design pattern called explicit typing, and that entails typing through properties. And the idea of doing this, which is quite clever in many cases actually, is that it allows you to add your custom data types without modifying the ontology. So the example on the right-hand side, instead of saying that room has the subclass office room, we can say instead that room has type, and then there's a room type, and room type has a member individual, which is office room. So this allows us to do typing using other primitives than the OWL class hierarchy and RDF type. And this can be quite clever because you can add and remove these types using just your data, using your ABOX. However, if you do this and then try to translate to another representation model, your translator tooling will need to be adapted to this design pattern, not just in the general case, but actually in every instance of this design pattern. You'll have to wire up your translator tooling, which is inelegant. And also, if you do have a set of pre-populated types, such as office room here, and you want to translate this into, say, source code, it's not immediately obvious how you would translate that data into a representation that works for your output, right? So, you can't translate it into objects, right? You'd have to translate it into some other representation. Could work, but could also be tricky. So this design pattern is probably not good for these types of use cases where translation is involved. Principle 4, avoid property inheritance. Right, so many formalisms of data modeling do not support the notion of subproperties or subfields in the same sense that OWL does, where instances of a subproperty implies instances of the superproperty. You could conceivably shoehorn this into getters and setters or property methods on OOP languages, but it would be kind of ugly. Also, perhaps more importantly, it's quite common in ontology engineering to have restrictions on superclasses that are then narrowed by restrictions on subclasses. And I give an example here where you have collections that have members through a generic has-member property, and then you have a subclass book collection which has a restriction that it accepts only books through the has-member relationship. This is perfectly fine in OWL, but it's not easy to translate to, say, a programming language that doesn't allow you to overload fields or properties, right? So in such cases, better to avoid this design. Principle number 5 about property names. So this is actually a usability challenge here, in a sense, that ontologists tend to have reasonably long names for properties, such as the examples given here. And I'm thinking that may be because properties are in an OWL ontology their own entities and have their own identity and are shown in their own listing in Protege and other tools. Whereas in many of these other output languages that I exemplified with, properties are fields on a type of some sort. And therefore, the naming in those types of scenarios is typically more concise and tied to the name of the type. It's sort of implicit that the placement of a device implies the placement context of that device. And it's also a cultural thing, I guess, in how programmers have developed their schemas. Just look at any typical JSON schema or whatnot. So try to use short property names if you want to collaborate with programmers and use names that they are familiar with. Principle number 6, avoid global semantics on properties. Right, this gets a bit tricky, but basically if we're not going to specialize properties through inheritance and we're going to have short property names, we're going to end up with a situation where properties are kind of generic, kind of ambiguous. The example given here is, of course, has name there, where you might have the subproperties has person name and has corporate name that are connected to corporate individuals or personal individuals in a traditional modeling. But if we do this adhering to these principles, we'd end up with something more vague and ambiguous, something called perhaps a just name. And if we have that, then defining global semantics like domain or range or functional property and so forth on just name actually really restricts what we can do with it. So the idea here is that it is more flexible to apply such restrictions locally on the classes. And this also supports readability in Protege, as the example on the right hand shows. This is the semantics of, I believe, a pump of some sort. And this is actually shown on the definition of the class, of course, in Protege. So you see which properties are supposed to be used with it without having to go to another pane or tab in Protege. So from a usability point of view, this is helpful. Principle 7, be opinionated. So, ontologists tend to overgeneralize early, trying to solve every sort of problem and trying to be open and flexible. And the example from my space, the smart building space, is building taxonomy or building hierarchies, where you can view a building as being composed of, a building that has floors within it, and each floor has a number of rooms within it. Or you could say that a building has wings, and each wing has floors. And if I build an ontology for this, I may, as an ontologist, end up in a situation where I want to support both styles of modeling, because I don't know what the ontology will be used for, and I generalize. And I may also quite often use quite generic names for things like zone or agent or things like that. Whereas what the developers here want, typically, is one clear-cut data model for how to represent the domain of discourse. So they want, typically, for instance, to say that not that I can model the building in different ways, but there is one standardized way in which to do it. And that does not compose of zones that subsume other zones, but it composes of floors that contain rooms in a terminology that they are used to. So try and be opinionated and in line with the practices of the domain that you are modeling, if this is the type of modeling that you're doing. And 8, the last principle, OWL imports. OWL imports like functionality is not necessarily supported in target formalisms. It may be in some cases, but you may often need to collapse or import the entire transitive import closure, all the ontologies that you have imported, and collapse them into one model. And that can work just fine, but it can also lead to namespace collisions if the target representation doesn't actually have the notion of namespaces, or at least global namespaces, using IRIs like RDF has. And it can also, perhaps more importantly, be a bit usability-wise quite jarring, in that the different ontologies that you import are designed in different contexts and have, therefore, different practices regarding naming, documentation, design patterns, etc. And merging these all into one can end up with an ontology that looks quite ugly. So the recommendation, well, and quite inconsistent. So my recommendation here is that if you're going to be reusing ontological resources, i.e. ontologies, that is of course good. But if you need to do that, import them and adapt them to the project-specific context. And that includes things like the documentation and the naming and the design patterns and so forth. This may, of course, lead to that you'll lose compatibility with the sort of the upstream ontology, if you will. So there's always an element of judgment here to whether that is suitable or not. Thank you. I think I've covered my 15 minutes of presentation. I'd be happy to take any questions and I think more like discussion towards the end of this session. Have a great day.